Hello, this is David Harper of the Bionic Turtle with a brief tutorial on the normal distribution, easily the most common, popular, and familiar probability distribution of all probability distributions. The normal is also called the normal bell curve, and occasionally you'll hear it referred to as a Gaussian distribution. That's Gaussian with a G. A Gaussian distribution is the same thing as a normal. It's just a little more technical term. Okay, to show you the normal curve, let me show you in practice. Oftentimes we'll use it to describe asset returns. Even as we use it, we typically know that it's a misuse, that it's sort of inappropriate to financial returns, but it's so convenient that sometimes we'll use it out of sheer convenience. It has elegant and convenient properties. But just to show you why it's a misuse, here I pulled periodic returns for Google's stock price. This is ending mid-December of 2007. So these are the daily periodic returns that I've then plotted onto a histogram or frequency chart. And so you might say at first glance, well, that looks like the normal bell curve, and if I collected more data I would definitely get a smoother distribution. But if I superimpose the normal density function, so here's that bell curve plotted in blue, if it's for most financial asset returns, I'm not going to get a good match. So Google's pretty typical here in the sense that there's not a match. You can see the normal curve is symmetrical and clean, whereas my Google returns, well, first of all, they are positively skewed. See how there's a positive skew over to the right, leaving the space here? Secondly, what's harder to see is Google has some, because I have a thick blue line here, Google has some real outlier returns here on the positive side. The actual asset returns are typically fat-tailed. They have fatter tails. Technically, that's called leptokurtosis. So now let me take a closer look at the normal distribution density function. So here it is plotted. The plot is an implementation here of this formula, which has pi in it as well as the natural E. That has a value of about 2.71. In addition to that, really, there are embedded the two parameters that we need for the normal distribution. Here's volatility. That's that measure of dispersion, or that second moment measure. We need that. And here's Z, a standardized variable that is a function of the mean and the standard deviation. So embedded in the Z, we've got the mean and the volatility. Those are the two parameters we need for the standard deviation. I've got a mean here input, and I've got a standard deviation here of 1. So I have any numbers in here. I'm going to go ahead and put in standard values. The standard normal distribution, by definition, when I say standard, it means there's a mean of 0 and a standard deviation of 1, such that my x values here equal my standard variables, and then I can plot this normal distribution. This is a density function, also called probability mass function, here over to the right. So as you can see, I've done that two ways. First, here I use the built-in Excel function, equals norm dist. Takes four parameters. First, here where I've got B7, first it takes the x value, so that's the value of x on the x-axis. It takes the mean, which I've got a 0. It takes the standard deviation, I've got a 1. And then it takes a true if we want a cumulative distribution, or a false if we want the density function, which we do want. So that's my function. That's my straight use of the Excel function. And then just to prove to you that the formula is correct, here, instead of a function, I've got a formula. And that formula right here matches this. So it gives me y as a function of x, the standard variable here. In this case, for this first point, it's a -4. So that -4 is my z right here. Having that, and then also accessing also using as an input my standard deviation, I solve for y, which is then going to be that probability here. So that's that y-axis value here, a y value here. So here's the formula which implements this, which is equivalent to the built-in function. And that gives me, now I've got a mean of 0 here, but if you watch this chart, I'm going to just change the mean to 10, for example, and the curve doesn't change at all. The curve's very well behaved that way. but the mean changes to 10, and now I'm going to change the standard deviation to 5, for example. So watch the chart. Well, okay, it's hard to see. The x-axis changes, but this the x-axis changed, so the dispersion became greater, and I'll change the standard deviation back to 1. But I can change the mean of the standard deviation. The point of this that I wanted to show you is that I only change those two values. One of the characteristics of the normal distribution is that it's fully described by only two parameters: the mean, that sets the peak of the curve here, and the, what I've been calling interchangeably, the volatility of the standard deviation. That's the measure of dispersion or scatter that tells me how wide this is. That's it. Aside from that, this tendency of the tails to be skinny relative to real returns, that's just a weakness or flaw of the normal. So another characteristic is we have these rules of thumb, which you may have seen before, that refer to area under the curve. So if I just look back at this, this is the density function. The cumulative function is implied by the area under the curve. So if we talk about how much area under the curve goes plus or minus 1 standard deviation to the left and right, well, then we have these rules of thumb. About 68% of the area under the curve is covered by plus or minus 1 standard deviation. About 95.5% is covered by 2 standard deviations. About 99.7% is covered by 3 standard deviations. So those are rules of thumb that tell us how much of the area under the curve is covered by the distance plus or minus 1, 2, and 3 standard deviations respectively. So finally, before I finish, let me just explain the properties of the normal distribution. First, it's continuous, it's not discrete. Notice this line is solid, not dotted. Technically speaking, if I want to check for the probability of value, I have to check an interval because there are an infinite number of points on this line. That would be as opposed to a discrete variable or discrete distribution such as the binomial or Poisson. As I mentioned, second characteristic, there's only 2 parameters, fully described by mean and volatility or standard deviation. This makes it very convenient and handy to use. Many distributions are more complex, require more parameters, and therefore subject to, well, just more model risk or input variation. Third, we say the normal is symmetrical. It has technically it has a skew of 0. Fourth, we say there is no excess kurtosis. There are no fat tails. The kurtosis, therefore, on the normal is going to be 3. So we say the kurtosis is 3 or the excess kurtosis is 0. Same thing. Why is it so common? Well, there are really 2 reasons, and I would argue there are only 2 reasons. There is nothing inherently special about the normal distribution. It is not necessarily appropriate for risk metrics, and nothing elevates it to any special importance in the study of risk, simply because risk is concerned with the tail. The strength of the normal is about the central tendency. The 2 reasons it's common are, 1, it's easy due to these parameters, and 2, this is very profound, the central limit theorem. The central limit theorem says the sampling mean of the samples tends toward become normally distributed. Well, that is a statement about the central tendency of the normal. It's not really a statement about the tails and the appropriateness of the tails. Therefore, it's not doesn't necessarily have any special significance in the context of risk. But the central limit theorem does explain why it's so prevalent as a distribution. So this is David Harper of the Bionic Turtle. Thanks for your time.